Ladies and gentlemen, welcome to Chemistry 101.
Your hair's so oily, go wash it now!
My hair feels so silky and soft. With soap, my hair is no longer greasy. Oh god, it's so hot here. Oh my no! What do I do? It refuses to come off. What should I do?
Try so.
Huh? Who said that? Who said that? Was it you? Wow! It's completely clean! So, how does soap work? But in order to understand how soap works, we first have to understand how soap is made.
The term saponification is the name given to the chemical reaction that occurs when vegetable oil or animal fat is mixed with a strong alkali. The products of the reaction are soap and glycerin. Saponification is a process that produces soap, usually from fats and lye. In technical terms, saponification involves the base, usually caustic soda, NaOH, hydrolysis of triglycerides, which are esters of fatty acids, to form sodium salt of a carboxylate. Depending on the nature of the alkali used in the production, soaps have distinct properties. Calcium hydroxide, CaOH2, gives hard soap, whereas when potassium hydroxide, KOH, is used, a soft soap is formed. Soap allows otherwise insoluble particles to become soluble in water and then be rinsed away.
What we have here is a container of two immiscible liquids, water and oil. As you can see, they do not mix. Let's see what happens when you add some washing powder into this mixture. As you can see, the oil and water have mixed together to form a cloudy suspension. Oil and water no longer exist in its individual layers.
Washing up liquid is a kind of soap. Normally, oil and water don't mix, so they separate into two different layers. Soap breaks up the oil into smaller drops which can mix with water. It works because soap is made up of molecules with two different ends. One end of a soap molecule loves water, they are hydrophilic. The other end of the soap molecule hate water, they are hydrophobic. Hydrophobic ends of a soap molecule all attach to the oil, while the hydrophilic ends stick out into the water. This causes a drop of oil to form. This is because the hydrophobic end, being non-polar, will react with the non-polar dirt. The electron density distribution in molecules, including non-polar one, is not static. Therefore, as a function of time, the electron density is not uniform. Occasionally, randomly, the electron density in a molecule will shift to produce a spontaneous dipole. Part of the molecule now has more electron density, delta minus, and part of the molecule now has less electron density, delta plus. This spontaneous dipole is temporary. This spontaneous dipole also have a propagating effect. If molecule A, the hydrocarbon chain of soap molecule, develops a spontaneous dipole, then the electron density in the neighboring molecule B, which is the oil and the greases, will respond by developing a spontaneous but opposite dipole. The delta plus region of B will be close to the delta minus region of A. This new dipole in B is an induced dipole. This induced dipole in B will then induce a new induced dipole in another neighboring molecule. By this time, the temporary dipole in A is already fading, perhaps to be replaced by a new induced dipole from another molecule. These random, temporary, but continuous propagating dipoles have attractive forces, which is known as the dispersion forces. The magnitude of these forces scales with increasing surface area of the molecule. Thus, larger molecules will have an overall stronger dispersion forces than smaller molecules. Why is the hydrophilic end able to form bonds with water? In water, the hydrophilic end contains sodium or potassium ions. These ions float freely, leaving a negatively charged head. The water, being a polar molecule, is able to form bonds with the ions through an ion dipole attraction. It is an attractive force that results from the electrostatic attraction between an ion, which is the sodium or potassium ion, plus a neutral molecule that has a dipole. In this case, is water. They align so that the positive and negative forces are next to one another, allowing for maximum attraction. Like a dipole-induced dipole force, the charge of the ion causes a distortion of the electron cloud in a non-polar molecule.